Thank you very much. It's a great pleasure to be here and a great honor. And so when I was asked to come, I gave a very serious title. So it's not in the, I've changed it. So now I think it should be, because when you work in nonlinear physics, there are various possible addictions. And I think quite a number of people in the room have the same investigating Faraday waves. So you'll hear many talks about that. So Faraday waves are done in a very, basically the experiment is very simple. You have a bath of liquid and you shake it vertically, and Faraday instability produces surface waves. And in general, that at near the threshold, it gives a sort of square pattern of waves. And if it was only this, it wouldn't be very fun. So the theory has been done a long time ago, and this is when it's a non-viscous fluid, and you have several tongues, resonance tongues, due to forcing of the surface, and in all of them the waves have a subharmonic frequency as compared to the forcing. Okay. So, in fact, this is a non-viscous fluid. If the fluid is viscous, there is a threshold, and this was involved. This was done by Laurette Thuriker here, and she has shown that there was a finite threshold under which the fluid is stable, and you have several tongues. And the most unstable tongue is the one where the waves have the frequency half of the forcing frequency. So if you're near the threshold, you have linear waves, and if you go here, you have nonlinear waves, and you can also be below the threshold, which will be our experiments. So this is the basic stability. So of course, what is fun is nonlinear effects, and nonlinear waves in Faraday instability were entirely mastered by J. Feinberg. And he found a large number, an enormous number actually, of possible patterns with a forcing with one frequency or several frequencies. And this is the most recent of his papers, but he has also written a big overview of this nonlinear pattern. Another fun thing to do is to find for localized mode, and this was first done by Harry Sweeney and his group using sand instead of a normal fluid, in which case you have a very strange effect where you have a small area of the sand that oscillates with large amplitude, like a small volcano, and it's completely isolated. And these are called oscillons. And Jay found them in various conditions, either using strange fluids. The idea is that the Faraday threshold is better to be subcritical. Now, this is one case where the oscillons are motionless, but Jay also found a very interesting regime in which the oscillation region is propagative, and he has these strange looking structures that move on the bus. Okay, so the fun was fun long time ago actually, and the first to enjoy Faraday waves alligators. Alligators for seduction bellows, and the bellowing is strong enough to generate these waves with such a large amplitude that they create droplets. Okay. So we became also adept in Faraday instability in a much more quiet way when we found with Emmanuel Faure and Suzy Protière that you could bounce a drop on a liquid bath if you vibrate it vertically. And there are some so in fact the idea is you put a drop of oil on oil, and you bounce it by vibrating the bass under it. And in fact, there are several regimes of bouncing. In one of them, the drop bounce at the frequency of forcing. And the trick is that there is a small film of air between the drop and the bass, so that the drop never coalesces. So in fact, there are several bouncing regimes. Either the drop bounces at the forcing frequency, or the bouncing itself can undergo period doubling, at which time the drop bounces in one period out of two. And in this regime, the drop becomes propagative. And you can see, maybe this is a film I can show you. This is a regime of a walking regime, where this is a slow motion, and you see the drop moving from left to right, because it bounces on the waves that it has created previously. So these things that got us busy for a long time. And as you see, if you look from above at this object, you have a drop bouncing here, and this is a wave field associated to it. And the wave field has been entirely created by the drop, and it has accumulated because of the trajectory of the drop. So in this case, the drop moves at constant velocity on the bass, and it forms a sort of coherent object, since the drop only moves because the waves are there, and the waves are there only because the drop created them. Because you must remember that these experiments are done below the Faraday instability threshold. So there would not be no wave if there was no disturbance by the waves. Okay, so the problem is, what is the structure of this wave? What is the nature of these waves? So in fact, we did a very simple experiment, which was aimed at understanding what is the nature of this. But you would not like to know what wave is generated at each bounce by the drop. But the drop bounces repeatedly, so you would like to have only one bounce. So instead of using a drop, you use a small steel ball, and you just drop it in the bass to see what wave is emitted. So this is a very simple experiment. You take a steel ball, you drop it, and if the bass is at rest, you see it creates a wave, and this wave propagates a wave. This is exactly what you get if you throw a stone in a pond. You have a propagating wave moving away from the point of impact. Now you do the same in an oscillating bass, a bass that is below the Faraday instability threshold, and you see the same propagative wave being emitted, and it leaves behind a pattern of standing waves. So these standing waves are Faraday waves, and you can, by looking at the evolution of a cut in this direction, time evolution, you can find a spatial-temporal. This is a spatial-temporal analysis of the wave. This is the point of impact. Time goes on downward. This is the wave propagating waves that is propagating away from the point of impact. And you see here a pattern of standing waves that decay away slowly on a typical time scale tau. Okay, so you see that saying that you have a standing wave here means that you have two propagating waves counter-propagating, one out from the point of impact and one coming from outside. So where does this wave come from? How can you understand this? Is there other situation in which you can have sort of waves coming back? And this has generated very interesting set of experiments. I was not directly involved in them, by Vincent Bacot, Matthias Fink, and Emmanuel Faure. And the interesting with surface waves is that unlike light or sound waves, you can change the index of refraction, the velocity of propagation of the wave during its propagation. You can affect the medium in real time. So in fact, for instance, suppose you have a propagating surface wave and you tune down gravity, then the return force disappears. And what happens? So this was investigated by Emmanuel Faure and Vincent Bacot, and actually the film. So they have here a small impinging jet of air on the surface of liquid, and they just do one fast perturbation of the surface. So as you see, you have a wave propagating away, and then they will at one point suppress gravity here. And as you see, as they have suppressed gravity, you have a wave propagating backward and returning to where it comes from. So this is the reason for that. I can play it again if you want to see it. So you see the wave propagating away, then you do a jolt on the whole bath that creates a zero gravity, and as you see, a wave comes back. So it means that during the jolt, gravity is zero, so the disturbance of the surface remains. The surface remains disturbed, but when the gravity is returned, the wave, so to say, has forgotten in which direction it was propagating, and you get two waves, one what propagates in the initial direction, and one propagating downward, inward.
Question.
Yeah.
So during the jolt, does the gravity go to 0 and then 2?
Well, in fact,
and then 1?
It can either go to 0 or it can go to a high value. It doesn't change. The main thing is to change brutally the index of refraction. Okay, so this is the what you see. This is the time processing of the wave. The wave is created here. It moves away. This is a jolt, and you see that during the jolt, a wave keeps propagating straight, and a wave returns to where it came from. So this is one case, and in fact it has. So the authors have called it a time mirror, in the sense that it is equivalent to a standard mirror is a mirror that reflects a wave in space. Here you have if you look at the propagation of wave as a function of time, you see the wave propagating out from the source here. Then during this jolt, there is no propagation. And then two waves propagate, and one of them refocuses on a focus which is not a virtual one as in a real mirror, but a real one. So it can lead to rather spectacular time reversal behavior if you have a complex source. So this was done to show that it was done in France, of course. So here you have the source. You have a source made of many, many little sources that are spread out in the shape of an Eiffel Tower. So you have little jets here of air. They will disturb the surface. You will see the wave propagating out, and then they will impose a jolt. So this is a simulation of the same thing. So you see here the wave propagates. They're quite complex structure. No jolt yet. Now they have a jolt now, and as you see, the wave starts reconverging, and in the end, you return. You have the inward moving waves that reconstruct the initial source. Of course, there's always a wave moving out that is lost in the distance. So with this view, this opens a way of understanding the Faraday wave in a slightly different way. It doesn't tell you anything new about Faraday wave. It's just a different way to look at them. You can see that the parametric forcing in Faraday wave, you modulate G. So you modulate the velocity of propagation. If you wish, it is as if you modulated the index of refraction of a medium while a wave is propagating. So in this so if in this analogy, if in the normal optics you have these Bragg mirrors which correspond to a spatial modulation of the index of refraction, here you can see the Faraday wave as being the Faraday forcing as being a temporal forcing of the index of refraction, and this temporal forcing of the index of refraction gives rise to a reflection of the wave. So they move back, and this was actually shown by Vincent Bacot in an experiment which I find very clever. So he has a Faraday bath with a special shape. Here is a shallow region in which the Faraday waves are not generated, and a deep region here where the Faraday waves are generated. He has a pulsing source here which generates propagating wave in that region. And during this, at first, there's nothing, the thing is not oscillating, so the wave propagates away. And then they start the vertical oscillation of the bass, and therefore, this trigger Faraday waves in this region. And this is what you see. So you see this is oscillating source, nothing happens, there's no Faraday effect. Then they stop the source at one point, and they start the Faraday forcing here. And as you see, the Faraday forcing generates a wave that goes out of the deep region of the bass, and that goes to converge to the point of emission. So you can see that you have managed to have a sort of reversal just by a Faraday modulation. Okay. So in fact, so why did I say this? It's because in general, when you think of pilot waves, when you think of a system being piloted by waves, you think of animals, you think of bats, of dolphins, and in both cases, it is emission of a traveling wave that moves away, and by the reflection of these pulses of waves, the brain of the animal analyzes the reflection and understands where the obstacles are. But this is linked with standing wave, with propagating waves. In our case, our drop is associated to is piloted by a wave, and this wave is a standing wave. And strangely enough, a standing wave had been considered by De Broglie in very early models of quantum mechanics, where he had said that you could have a particle associated to a standing wave. And he saw that, so he thought of not of a statistical wave, but of a physical wave associated to the drop, to the particle. And he thought that there was a problem because he would have this term of advanced wave coming back to the particle, which, as he said, was posing interesting philosophical problems. So anyway, in our case, in our experiment, the advanced waves are not mysterious; they just come from the Faraday forcing. Okay, so now let me return to the experiment and to its numerical simulation. So I will go into the detail of how can these walkers, as we call them, can be modeled. So you remember this. So this is the shock at one. So at each collision with the bass, the drop creates a disturbance. This disturbance propagates away and leaves behind this J0 Bessel function of standing waves, which is damped on a typical time, which is linked with the distance of Faraday instability threshold. Okay, so if you want to model the motion, you have to understand that the drop moves because it is driven by the wave, and you have to compute the wave which is created by the drop, but not instantaneously, but by the drop motion, previous motion. So in fact, if your drop is moving along this trajectory, you have to assume that at each point of this trajectory, it has created a Bessel function, and the whole wave field here will be created by the superposition of this Bessel function with a damping term, which tells you how many sources you have to consider in the past. And in this point, so this number of sources can be either small or large, and in this point you have to compute the slope, local slope of the bass, and the drop will hit the bass and then move forward as a function of the local slope of the bass at the point of impact. So this is what we do. So this is the motion of the drop. The drop just moves up and down because of vertical acceleration. And at each time it hits the bass, it receives a forward kick in a direction fixed by the local slope. And this local slope, of course, has to be computed from the wave field that you have computed before. So this leads to a numerical simulation of the bass of the wave field. This is a numerical simulation for a case of a drop moving straight with a long memory. And as you see, the interference pattern can be quite complex. And it reproduces well what is observed experimentally. So, in fact, in the experiment, the nice thing is that you can tune how many waves are involved in the motion of the drop. If you are far from Faraday instability threshold, you are far below the Faraday instability threshold, in that case, the waves are strongly damped. Therefore, only a few waves survive, the most recent that have been emitted, and you are in a situation like this, which I will call a low memory situation, where the wave field is quite simple, being only created by the last few collisions with the bars. In contrast, when you are near the Faraday instability threshold, you are in a situation which we call long memory, which means that you have to take into account the waves emitted in the last 50 bounds to compute this field. And as you see, it has a more complex structure. It's not so important if the drop moves in a straight line, because it doesn't feel what is happening behind. So the question that arises is what happens if the drop revisit regions that it has already disturbed in the past. So these were what I'm going to discuss in the rest of the talk. So we'll discuss situation where you have the orbits of the drops. So you can generate the orbits either by having a force transverse to the motion, this with either magnetic field or rotation, or a central force. And therefore, with this, so I'm going to describe what is observed if you force a walker to have an orbiting motion, respectively, at low memory and high memory. Okay, so the trick is quite simple. Inside the drop, you put a little bit load of ferrofluid, which is which can become magnetized if it is submitted to a magnetic field. So when it is in a constant magnetic field, this small oil drop becomes a small dipole. Now, on the magnetic field, you superimpose a second magnetic field, which is centered, which is maximum here. You have a small magnet here. And so you have a gradient of magnetic field, and therefore the small dipole will be submitted to a central force toward the point below the magnet. So this is the way this experiment is implemented. This is a vibrated bar. This is a small drop. There is a magnet here, and this magnet, the height of this magnet can be tuned, and this changes the profile of the magnetic field. So why do we do that? So depending on the height of the magnet, the potential in which the drop will move can be either wide or narrow. And this is what we are going to study, to tune. So why do we do that? See, in this system, there are some strange effects that are somewhat reminiscent of quantum physics, but of course to a certain extent, because it's a classical system. So one of the things which would be beautiful to observe is quantization of energy. And in this system, there is no possible quantization of energy because the walker has a constant velocity and has a constant wave vector associated to it. So if you wish, the energy of the walker is fixed. So there is no way you can see in a potential well different levels like this. So there is nothing, this is not possible to do with this experiment. What you can do is change the potential well in which the drop is enclosed, tune it, and see if something special occurs for certain widths of the potential well. So this is what we can do, the walker being unchanged. So we did do that. Okay, so the first experiment is to see if the experiment works. You just put the walker at low memory, so far from the Faraday instability threshold. The waves are very localized beneath the walker, and it walks at constant velocity. since its velocity is constant, the only natural trajectory in a central field is a circular trajectory given by the classical laws of mechanics, and with a radius that changes continuously as a function of these lambda parameters. So this lambda parameter is the width. The frequency is linked with the frequency of this potential well. So in this case, everything is normal, nothing special. The drop moves on a circular circle as expected from the laws of mechanics. But then now you can tune up the excitation so that the Faraday waves are sustained for a longer time, and therefore during its motion the drop will create waves all the time during the whole orbit, and it will have to move in the field that's created in the past. So what are, in those conditions, the possible trajectories? Well, with long-term memory, you get typically this. So you have this quite circular orbit. You tune up the Faraday forcing. The waves are sustained during a longer time. And as you see, if you do nothing special, genetically, the trajectory becomes strongly chaotic. Okay, so then you look a little bit more carefully and you fine-tune the distance of the magnet to the surface, and you see if you see anything special. So this is just a view of the chaotic motion with which gives you an idea of the drop and the origin of its chaotic motion because of the complex structure of the associated surface field. Okay, so if you tune finely the width of the well, you find that for certain values of this width, you recover stable trajectory. But these values are very sharp. They're it really needs a fine tuning, and this is what you observe. For even though the system is at high memory. So it means that this is the memory and this is the radius. For low memory, any radius is possible, and for large memory, only discrete values of the radius are possible, characterized by a number which is linked to the ratio of the radius to the wavelength. Okay, so the surprise comes from the fact that new types of orbits show up that don't exist at low memory, and that are in the shape either of lemniscates like this or of trefoils. And again, these possible, so there's still one more which is formed of small loops with a stem like this, strange, but it is also a stable trajectory. And all these stable trajectories are only observed again in very, very narrow range of values of the control parameter. So you can try to characterize them all. So you characterize them by the mean size of the orbit, which is in a way somewhat equivalent to energy, and then the mean angular momentum, on the meaning averaged on one orbit. Okay, so you do that, and you look at what are the possible values. These are the function of lambda, the width of the potential well, and these are the successive circular orbits. These are the lemniscates, these are trefoils, and this angular momentum as well is quantized. So instead of plotting the mean radius as and the mean angular momentum as a function of the width of the well, you can plot them as a function of each other, and in which case you find that the stable orbits are characterized by two numbers, one which is linked with their size, the first one here, and the second one which is linked to the angular momentum. Okay, so you have a first level here, second one, third, fourth one. And of course, this is symmetrical because you can have rotation in one direction or the other. So this is, can be simulated in a numerical simulation of the type that I've shown you. And it is somewhat similar to what is observed in 2D harmonic potential quantization condition in real quantum physics. But of course, this is cheating because in our case, we don't have energy, we have size. Okay, so the origin of the double quantization can be understood in this fact that as a drop orbits on its orbit, it keeps generating waves, and these waves accumulate. And so it's a little bit like if the drop was moving on the drum, it would generate global oscillation of the drum. And this oscillation can be analyzed by having the wave field, the global wave field, projected on a base of Bessel wave function, not generated at the point of the drop, but at the center of the orbit. And when you do that, you realize, so this can be done because there is a theorem, graph theorem, which was revealed to us by Mark Meskin, which allows this development on a base of Bessel function. And if you do that, you realize that, for instance, the global field of the drop moving on its first circular orbit can be projected and as this this component with a very weak J0 Bessel function, a very strong J1 Bessel function, which drives the motion, and a very weak J2 Bessel function. And in fact, you realize that if the drop, the radius of the motion, so this is the amplitude of the J0 Bessel function generated by as a function of the radius of the orbit. So if it is coincide to the nodes of the Bessel function, when you hit a drum on its nodes, you don't excite waves. So, but if you hit it near an antinode, then you excite waves. And you see the drop during its rotation motion. If it is rotates on an orbit which coincides with a node, then it excites no wave. But it excites wave of opposite sign if it is slightly larger orbit or slightly smaller orbits. So this means that you create a potential well. So this additional potential well is the well corresponding to the additional force created by the wave and acting on the drop. When the drop is in those regions, it has a stable orbit and there is no extra force. And if it has a wrong radius, then there is an additional force. And this explains why these orbits become discrete. This is the experimental observation, and this is the numerical simulation of this effect. Okay. So we, after all, have found that indeed, when you change the potential well, there is something special happening for certain specific widths of the potential well, and that determines these stable modes. So, of course, the question is, what is special about this? Can you say that these special modes, the stable orbits, can they be described as eigenstates? So, of course not. I mean, a priori, they don't look like eigenstates. So, but you can look at revisit the complex trajectory. So this is the case where you have Hill-tuned system. So the trajectory of the drop is this mess. And you wonder what is the nature of this mess. And in fact, when you look carefully, you realize that this mess is, during the motion in this mess, the drop sometimes have a motion along one of the special orbits, either the circular orbit or the lemniscate shaped. And in fact, if you do a time recording, for instance, of the angular momentum, you find that it oscillates there, meaning that you're on a lemniscate, and then it's stable because you're on a circular orbit, then it oscillates again. So you have an intermittency. And at each, so in fact, what is interesting is that you have very little time of switch from one mode to the other. So in fact, at each time, the system is in one of the orbit, and it spends very little time, and so you can define a probability of being in one state or the other. So in fact, we looked in this region where you have no stable mode, and what we measured the probability of being in a meniscate and the probability of being in a circular orbit by looking at the time, by looking at the time spent in each. And what you find is that you can, when you tune this potential well, you change continuously the probability of being in one state or in the other. Now, the interesting thing also is that, so it means that at any given time, the system is only in one of the states. What is defined when you tune the system differently is that you change the probability of being in one state or the other. And if you imagine that you would be in a system where you cannot see the drop and you cannot measure its trajectory, well, then if you had any blind measurements in which you would be able to measure, say, the angular momentum, would give you one value or the other. And so you would have some kind of thing which is somewhat reminiscent of wave function collapse. Yeah?
Can you change the switch time between the modes? What does it depend on?
No, the duration of the time spent in each mode depends on the memory. The larger the memory, the shorter the time in each mode. But the time of switch, we don't know. We didn't measure.
It's random, right?
It is, but it's usually short compared to the time spent in each mode.
It has some average, but there is a distribution.
Yeah. Okay. So it means that so you can see the system as a memory system. So, and it is a strange system where you have an information loop that links the droplet on its wave field. You can see the system as being at each collision, the drop writes an information on the bus by creating a Bessel function. Then this information is sustained because your Faraday forcing sustains the stranding waves. And then the drop goes in the air and falls back. And when it falls back, it reads the information that it had deposited before. And so one question is, can this memory be read either by another drop or by the drop itself backward? Or can the memory be erased? So this I won't have time because I was waved. So you must just remember that both the motion of the drop and the motion of the bus are subharmonic. So you have two types of possible drop on a given side, on a given bus, because they can bounce either during phase A or phase B. But the trick is that you can change a drop which is red, you give it a jolt again, and then you change it so the A drop becomes a B drop, so to say, but the field doesn't have time to change. And so we did this experiment, and this is what you see. So what you will see, so this is a stroboscoped image of the drop bouncing. It moves forward. At one point I give a jolt, so the drop changes phase and falls on the bus at the wrong phase, so to say. And you will see what happens, hopefully. Oh, sorry. So yeah. Okay, so it moves. And here, give a jolt, and as you see, it goes back. And it goes back on its previous trajectory. Okay. So as you have seen already, is it a trivial effect or not? Well, if we are on a stable orbit, it is trivial. It just means that you have changed v to minus v. So it has no interest whatsoever. But it also works in this regime. So in fact, I don't have time to show you, but you can check that the distance of the two forward moving motion and backward moving motion remains coupled for a time which is of the order of half the memory time. So in fact what happens is that the drop moves forward, then as it comes back it will read the same information deposited before with the wrong phase, so it will move back, but it will emit new waves which are the wrong phase, so it will erase the previous field. So I can show you this. Yeah, this is just for the mathematician, but I can answer a question afterwards. So you see, if it moves forward and then backward, it will erase the field. We looked at the energy, global energy of the field in a very chaotic motion. This is the global total energy of the field. This is a jolt, and as you see, it goes down before climbing up again. And this is the region in which you have the motion going backward. So in fact, this is just this I have shown you, and in fact, indeed, the memory can be erased. And in a way, you can see this system as being a sort of a Turing machine, except that the information is coded in a wave field. And the coding in a wave field gives it strange properties. Okay, so what is interesting I find in this system, it is a system of self-organization. Usually this term of self-organization is used for a system with many entities. You know, you have many bacteria, or many insects, or many birds, and so on. Here you have a system where you have a self-organization of one entity with its own past. So it's what we do every day in a way. Okay? And so in fact, it is also not only biological, it's also social entities, you know, large communities, countries, have a history and self-organize as a function of their own history. And contrary to what is usually thought, that the influence of memory is not stabilizing. It can be destabilizing and drive to extremely chaotic behavior regimes. But strangely, out of this come effects that are somewhat reminiscent of the wave-particle duality. Okay, so happy birthday, Jay.
The fact that you have a chaotic orbit that is spanned by the periodic orbits is very generic in dynamical systems.
Yeah.
And we know also what is the probability to see every periodic orbit, every unstable periodic orbit. It's inversely proportional to its Lagrange multiplier, to its Lyapunov exponent.
Yeah.
You measured probabilities, but you didn't measure the Lagrange multipliers. But I bet that they are going to be determined by the inverse of the.
We did measure. Well, so we.
Why say Lagrange?
As you know, it's difficult for experimentalists to measure real Lyapunov experiment, especially in this system, because it depends on memory. It depends on memory. So Stéphane Perard did an attempt of that by looking in. So he did very, very long recordings, and he looked at a region where you had the same trajectory for some time and where they had diverged. And he looked at the divergence and a typical time of divergence. And this works in the sense that you remember these tongues of stability that I have for certain orbits. Well, you measure positive Lyapunov exponent exactly in between those tongues, and you can measure them quite accurately.
And it's true that the probability is inversely proportional to the.
Yeah, this I don't know. It would be interesting to see.
That's what it is in the dynamical system.
Yeah.
Very possible.
Very cool stuff. I'm wondering what happens if you add more complex systems, so you have two bouncing particles. How would that change those?
So we have.
Or more complicated experimentally, but numerically it could be done. Perhaps to have two surfaces with a single particle bouncing.
Yeah. I can see the entanglement coming dangerously near. Okay, so with two particles we did some things that were nice, but had nothing to do with entanglement. So it was initial work, that of course when you have two particles on the same bus, they both have create their waves and they interact, and they have orbits, and they have common orbits which are somewhat similar to those, and that are also discrete. As far as entanglement goes, if I knew how to do it, I would, but problem is that the two drops are synchronized by the forcing. At least in some regimes. So maybe it is not that synchronized, so there could be interesting effect in the regimes where it is not too well synchronized, but for the time being we don't know. But it, as a remark, it took some time before between the EPR paper and Aspey's experiment. So maybe one needs a little bit more, and maybe also input from other people.
Okay,
There was
we're a
one.
bit late in time, so if you could keep the questions to the break, and we'll move on to the next talk. So thank you very much.